Okay. So good evening, everyone. Welcome to your 12th discussion session, or shall we share the final discussion session in Mechanical Behavior of Materials. I am Pragyandipta Mishra, a research scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. And today we'll be talking about three different topics: hardness testing, impact testing, and finally with mechanical behavior of composites. So with that, we'll come to the end of our discussion on mechanical behavior of materials. That is a part one of that course. Uh, if you are interested, you can continue on to the part two, where more discussions on different types of material behavior will be conducted, and there you can learn more about composites, etc. But here, this is the last class, and we will be ending our discussion for this course. Okay. So with that out of the way, let's begin about today's class. So first, coming to hardness testing. Okay. So before understanding how we do hardness testing or what are the various procedures involved in it, we need to understand why exactly do we need to look at hardness as a measure to look at material behavior, right? So what exactly is hardness then? How can we say something is hard or something is not hard? What exactly constitute as hardness in a particular material behavior? So we have been looking at strength in a different way, right? Like we have been looking at strength as the measure of material to take in stress, right? We have also looked at strength in terms of moduli of a particular material system. We have also looked at how a material system can take in different types of strain, etc. In those terms, we have been looking at strength, right? So essentially, what we have been looking at is the bulk behavior of material, right? However, it is not always possible for us to measure the bulk behavior of the material. Why? Because that test involves either it will be difficult for us to perform that test, or secondly, it might be leading to the product being destroyed, right? So sometimes you might want not to do like a destructive kind of testing in order to find out strength, right? So in order to understand, in order to find out strength in another way, what people have found out was you can also measure the material response to localized plastic deformation, uh, which will give you an indication of what is the strength of that material. Okay, so that is what they termed as hardness. And how they did it was basically they measured the material response to localized plastic deformation on the surface, and basically they measured it in different ways, and that give you an idea of what hardness of a material is and an indication of what the strength could be. Okay, so let's write it down. Hardness is a measure of the material's response Now, what kind of response this is? This is always resistance, right? The material will try to ensure that deformation does not happen. So, material response or resistance to localized plastic deformation on the surface. Okay, so this is your hardness. So now that you, give a second. So now that we understand what hardness is, how do we measure this hardness? Essentially, what we are trying to do, we are trying to deform the material or plastically deform the material at the surface level, right? So what are the different ways we can do that? So that will lead to types of hardness tests. So one way could be to scratch the surface, right? Essentially, you can scratch it using something and give a number based on that, right? You can scratch the surface. So that is known as scratch hardness. Another way could be to look at what will happen if you drop something on the surface. So if the surface is hard, if you drop something on the surface, the thing will bounce back, right? So this rebound could also give us a measure of what is the hardness. And another way could be we indent on the surface or we press something on the surface, and how much depth that thing could be pressed on with for a particular amount of load. If we measure, then we can get indentation hardness. Right? So these are the three ways people have discovered or people have over the time measured hardness in these three different ways. Okay. So if we look at so we have looked at what is hardness, what are the three types of hardness tests that people have identified. Then what exactly is the advantage of doing this hardness testing is first we should understand that, right? So why exactly are we doing this hardness testing? So benefits, okay. First one is of course simple and inexpensive, right? Compared to any other strength test. If you look at like tensile testing, compressive testing, shear testing, etc., those will be very, very complicated and they'll also be very, very expensive. Comparatively, this is very simple and inexpensive, right? So first one is simple and relatively inexpensive. Right. Second one, of course, if you think about it, this testing is non-destructive, right? Compared to any other type of testing, this testing would be non-destructive because only at the surface we are looking at what is the hardness. So it is non-destructive. And finally, it gives us an indication of strength, right? Without going into the complexities of other types of testing, this is an easier way that gives us an indication of strength. Okay. So let's come back to the three types of hardness tests, okay, and we'll understand them one by one. We'll be going in more detail about indentation hardness because that is the more modern or commonly accepted type of hardness testing in today's times. but we will also understand how scratch hardness and rebound hardness were being done earlier, and now why we have moved on to indentation hardness. Okay, so coming to scratch hardness first. So, what exactly do we mean by scratch hardness? Like, if we are talking about scratch hardness, by then, like, if you see the name itself, you can guess what exactly are we doing in scratch hardness. It's the ability of a harder material to scratch a softer material, right? So we are measuring the ability of a harder material to scratch right. So there is a scale known as Moore scale. Okay, Moore scale, and this scale basically goes from 1 to 10. Okay, and gives us an idea of how much is the scratch. Just a second. Okay. Yeah, so there's a Moore scale that gives us like a number chart which goes from like 1 to 10, and 1 being like the softest kind of mineral that we're testing, that is talc, 10 being the hardest mineral, that is diamond. Okay, so it goes from 1 to 10 and gives us a relative number from where between 1 and 10 the particular material lies. Okay, so there's a Moore scale. There's no apostrophe, this is just Moore scale, which goes from 1, which is talc, to 10, which is diamond. Okay, and in between, like, you'll have different materials. You'll have like gypsum, calcite, fluorite, etc. Till to like topaz, corundum, and diamond. So what you will do is you will take all these 10 steps, talc, diamond, etc. You'll make material out of it, and you will try to scratch a surface with these materials. Okay, so essentially at some point you will see that the scratch is till some point you'll see that the scratch is not happening, and after a point you will see that the scratch happens. So basically between, let's say you're taking a material like steel nail. Okay, so till 6 you will see that there is no scratch, and then the moment you go to 7, like quartz or something, then you will see that the scratch will happen on that steel nail. So you will know that the hardness lies in between the 6 and 7. So you will get a rough estimate that the hardness lies between these two numbers. Then what you will do is you will test it with other materials which have values between 6 and 7 against that, and then you will see, you will place them in between 6 and 7 accordingly. Okay, so this was a very convenient way to identify minerals. Okay, because you can easily take one mineral, scratch it against the other, and if you know the hardness number for one particular mineral, you will know that the other one is able to scratch or not able to scratch. Depending on that, you can put them at a higher or lower hardness scale. Okay, so this method was like very historically used like a long time back, but now like slowly this has been removed because this is not a very convenient way to keep track of which material is where. Okay, so the next method that we are talking about is rebound hardness. Okay, rebound So, like I already said, it is like a technique that is used to check whether a material bounces back when it is put on a surface, a hard surface, and what is the height up to which it bounces back. Okay, so you drop it from a predetermined height. You drop like something like you can drop a hammer. Okay, so here they drop like a diamond rounded tip hammer from some height, some predetermined height, and once it hits the surface, it bounces back. So the length up to which it bounces back is measured, and based on that, you can say that this is a surface is harder or surface is softer. Okay, so this is something like this. You'll have a setup like this. Okay, we'll put the sample here, and then a hammer is dropped from top. Just a second. Just a second. Yeah. Okay. So the hammer is dropped from the top, and you will have a scale kind of thing here. You will have a lot of numbers on this side, a scale being present on that side, and once the hammer hits the sample, it bounces back. Okay, so you will see that the hammer goes down and it hits the sample. Okay, and then it bounces back to some height. Just redraw this. Okay, so this height is what you will measure. What is the height, rebound height? So if we say that here it has, so this height is what we will measure. What is the height of rebound? That will give us the a value of hardness for this material system. Okay, so harder the material, higher will be the rebound. Okay, so simply put, this test also again gives us a measure, and it was like a very old test that gave us a measure of whether a material is hard or not based on how high or low the hammer bounces back. Okay, so this just like scratch test, this test was also used very like it was used like decades ago. Now these two tests have been replaced with indentation test because it is much more convenient for us to do the indentation test, and we are able to do it in several different ways, and that way we can actually get a much more clearer answer for hardness. Okay, however, one major advantage of this test was until today even is that this is much more portable and easy to handle as compared to any other test that we have for hardness, because you only need that small setup and one hammer. Okay, so you need a very small setup and you can easily carry it around and measure hardness anywhere. Okay, so this is something that you can remember. Portable and easy to handle. Okay, so now let's come to the new type of hardness testing, or basically the ones that we are doing today. Okay, the modern hardness testing types, which is known as indentation hardness. So as the name suggests, the concept behind indentation hardness is just that you take a specific indenter, if you could have a ball indenter, a cone indenter, or any other type of indenter, and you press it onto the sample, okay? And the depth up to which it is getting pressed in, okay? So you can measure it either as the depth or as the area up to which the indenter is able to press onto the surface is measured, okay? So you have a predetermined load which is set up, and that specific load only you will apply for every material system, and you will press the indenter with that particular load, and you will measure what is the area or depth up to which that particular material has been deformed, and that will give you a measure of hardness, okay? So essentially what is happening here is, you have, let's say you have a sample like this, okay? So you put the indenter, apply some force F, some predetermined force F, okay? And so I'll just mark it. This is your indenter. This is sun. Okay. So your material will deform by some amount. So you will see something like this. Okay, so this, either this depth or the area that is being occupied by this indenter will be measured, okay? And then you can measure hardness, something like, one way could be to just take the load divided by the indentation area. Okay, so that could give you the value of hardness for this particular system, okay? So this is the general concept behind indentation hardness, okay? So essentially, if you have for the same amount of load, the indentation area is larger for one particular system compared to other. So you will know that whichever has a lower area or lesser area, for lesser indentation area, would be more harder, right? So your H1 will be inversely proportional to the indentation area and directly proportional to the load carrying capacity, right? Okay. So in today's time, there are three different ways this indentation hardness is being done. Brinell hardness, Vickers hardness, and Rockwell hardness. Okay, so let's understand them one by one. So first, let's go with Brinell hardness. I think spelling is NEL. Okay. So in Brinell hardness test, what we have is we have a 10 mm steel ball, okay, or tungsten carbide ball, which is being used as an indenter. Okay, so it will be ball shaped. So 10 mm steel or tungsten carbide ball used as an indenter. Okay. Okay. Then the load that is being applied is also fixed. Okay, it's usually 3000 kgf or 3000 kilogram force. That is also fixed. 3000 kilogram force. So here what happens is essentially, again, just like last time, we'll have the sample. Okay, let me draw a much more simpler diagram so that so this is my sample. I put a circular indenter on top of it. Okay, so I press it down. The indenter, I pressed it down, and then when I remove it, so okay, the indenter is pressed down. Then when it is removed, what we will get is just you'll get something like this, some impression on the surface like this. Okay. Not very circular, but I hope you can assume. Yeah. So this is how it will look. Okay. So you will have some diameter D1 and D2. Okay. So the Brenner, so basically that D1 and D2 will be in two different directions. Essentially, most of the times you will expect them to be the same. Why? Why would you expect them to be the same? Okay. Why would you expect them to be the same? D1 and D2? Because it's a circular indenter, right? So your circular impression that it will form on the surface will most probably be same in all directions. Okay. But just in case it is not, to ensure that it is an average diameter that we're taking, we will just take D1 plus D2 by 2. Okay. So average diameter D is taken as D1 plus D2 by 2. Okay. So using this, we can find the Brinell hardness number as BHN, or Brinell hardness number as 2P divided by pi capital D in bracket D minus root of D square minus T square, small d square. So this is the Brinell hardness number. So here P is the load, right? So we have defined it already as 3000 kgf, but just in case you have to apply more or less, you can do that as well. Load in kgf. Okay. D is indenter diameter, capital D. And small d is diameter of indented impression. Okay. So the indented impression on the surface, the average value, like I calculated with D1 plus D2 by 2, right? The average value is small d. Okay. So this is diameter of indented impression. Okay, so this is in, okay, so small d and capital D are both in mm. Okay, so there are two major disadvantages for this method. Other than that, it is fine everywhere else. So two places where it does not work is it is not very reliable at high hardness value. Okay. Just a second. My screen just went off. But my screen is coming now. Let me check. Yeah, I think my screen is now back. So yeah, so like I was saying, it is not reliable at very high hardness value. Okay, that is greater than 400. Okay, greater than 400, we will not see uh, much reliability for this kind of test because we are using steel ball or tungsten carbide ball. So it will be very difficult for us to indent once we reach those high values. Okay, especially if you're using steel ball because steel ball is actually not that good in indentation. Okay, and it is not very suitable for thin samples also due to very large indent impression. Okay, not suitable for thin samples due to large indent impression. Okay, so what will happen in thin samples is if we are pressing it down too much, what will happen is the sample will bend or something will happen to the sample. Okay, so it will not just be an indent impression, but other kind of effect will also happen. That will also take place. So our hardness number that you will get will not be a very correct value. Okay, so you will not be able to measure it for thin samples. Okay, so next moving on to the second type of hardness testing, uh, which also follows the same uh, footprints of indentation hardening. Vickers hardness testing. Just a second. I think there's no apostrophe. Yeah, just Vickers. Okay. So here the main difference is that you don't use a ball like steel ball or tungsten carbide ball. Instead, we use a diamond pyramidal indenter. Okay. So this uses a diamond pyramidal indenter. Okay, so it looks something like this. If you see the side view, it looks something like this. From the bottom, we are trying to see how the indenter looks like. Okay, so let's say it is something like this. Okay, so at the bottom we'll have some 136-degree angle between the faces. Okay, so if we measure the angle here, it'll be like 136 degrees. Okay, so if I draw the side view, that will be more clearer, I think. If I draw something like this, so this angle that we are seeing, right? So this is 136. Okay, and it will create a diamond kind of impression on the sample. So this is my sample. Okay, I will see this kind of impression. A squarish diamond kind of impression. Okay, and then we'll have D1 and D2. Okay, this is a sample. So again, you can take average D value to be D1 plus D2 by 2, just like last time. Yeah, just like last time, you can take D1 plus D2 by 2 as your average diagonal length. It's not diameter because this is not circular, it is diagonal length. Okay, is D is equal to D1 plus D2 by 2. Okay, and so final hardness value, okay, or HV will be equal to 1.854 P times P divided by D square. Okay, so D is your average diagonal length in mm, and P is load in kg, just like last time. Okay, so this is Vickers hardness testing. Before that, we learned about Rockwell, so let me just put this as P. And then finally, we have Rockwell's hardness. Okay, so Rockwell's hardness testing is another way to automate the testing. Okay, so this was developed in order to automate the testing. So this usually has a conical indenter, but sometimes steel ball also people have used. But this is like an automatic way of measuring hardness. Okay, so how this works is basically something like this. So if we have a sample, okay, this is my sample. Initially, I'll apply a minor load. First, I'll apply a minor load to the sample. Okay, so some depth it will go in. Okay, so we will just call that depth as some depth we'll measure. Okay, then we will apply a major load. Okay, so that it goes down further. Okay, so we are applying a major load. So it goes down to some new level. Let's say the first level was A, this new level is B. Okay, so it has gone down to some new level B. Okay, then we remove this major load. Okay, so what will happen is it will come back. Now the system would come back to some value C, okay, to some height C. Now this A, that A and C, the difference between A and C, the initial position at which the indenter was due to the minor load, and the final position the indenter is due to the minor load, we'll measure. Okay, so that will give us the value of E. This thing will give us E. Okay, so this will be major plus minor, and this will be major removed. Okay, so essentially what is happening, step by step, if we write it down, first apply minor load. First apply minor load. Okay, after that major load is applied and then removed. Major load is applied and removed. Okay, finally the depth of the indent is measured at the first minor load and the final minor load. Depth is measured at first minor load and final minor load. Okay, so using that we can find the hardness. So what is the formula here? So this is a little bit different compared to the previous two tests, and here we have two different types of values depending on whether we are using a conical indenter or we are using a steel ball as an indenter. Okay? So if we are using a conical indenter, so our hardness value for conical indenter would be equal to 100 minus E divided by 0.002. Okay. So this is for conical indenter. And for ball indenter, it will be 130 minus E divided by 0.002. Okay. So E is the only value that we have to measure. And then we can find the hardness for this particular case. Okay. So here we can use, so let me just write it down. This is for diamond cone and this is for steel. Okay. So this is about hardness, okay, hardness testing. Now let's move on to the second part of today's discussion. It is impact testing. So hardness testing was one type of measurement that we needed to do, right, for some particular case. Why do we need to do impact testing? What is the idea behind doing impact testing? Now, all type of testing measurements or all types of strengths that we have checked till now was based on the fact that we are applying load in a controlled, structured way, right? What if the load is suddenly applied? What happens in that scenario? Okay, at a very high strain rate, we are applying load. Then what will happen? In that case, the material behavior will not be same as whatever behavior we are seeing for simple case where strain rate is smaller, or we have a very controlled way in which strain rate is being applied, right? So material will behave in a different way when impact load is being applied. And this is something that you would have observed in many places, right? If you are applying load slowly to some steel pipe or some steel structure, let's say, you are applying load slowly in the tensile testing machine versus if you take a hammer and hit it, there is a different kind of material behavior that you will be observing in both the cases, right? So many cases we have to apply impact loading, right? Like hitting something with a hammer, or like some particular product is being hit at very high strain rate, okay, in some particular application. So in those cases, we have to understand how that impact will affect the material behavior. Okay, so this is why this impact testing is necessary. So this is done in order to analyze the material behavior under very high strain rates. Okay, strain rates, or you can also call it impact loads. Okay, so where exactly do we actually, like, why exactly do we need this thing? Like, why exactly do we need to measure this? It gives us a measure of how ductile or brittle a material is, right? Because if a material fails suddenly under impact load, the material is very brittle. Okay, the material might be very strong, but just because it failed suddenly, we can say that the material is brittle. Okay, so brittleness and ductility has nothing to do with the strength part of the material, but it also governs material behavior in a way. Okay, you might have a very strong material but very brittle, so it might till the point it does not reach its ultimate strength or something, that till that point the material behaves very well, okay, but the moment it reaches, it collapses immediately. Okay, it does not show a slow deformation compared to ductile material. So therefore, in order to identify this ductile brittle material, impact testing is a very useful way. Okay, so there are conditions under which ductile materials also tend to show brittle behavior. Okay, so depending on different kinds of these different kinds of condition, we can say that a material might behave as ductile or brittle, and some of these conditions are as follows. Okay, so ductile materials tends to show brittle behavior under first is high strain rate, okay. So at high strain rate, you will see the ductile material behaving as a brittle because failure would be very sudden. Okay. So if you give a very high strain rate or impact load, the material will suddenly become brittle. Okay, it will fail very suddenly. Low temperature conditions also, it will behave in a brittle manner. And finally, when we are putting a triaxial state of stress by introducing notch in a particular material. Okay. By putting notch or some other kind of defect within the material that will produce a triaxial state of stress. Okay. So essentially, this impact testing that we are measuring is a measure of the notch toughness or impact toughness of a particular material. Okay. So, what exactly is happening in this test, impact testing? What exactly is we are looking at? Okay, so before that, I'll just write it up. Impact testing is impact testing or notch. We can just say it measures notch toughness. Okay, this is something that you can remember. Okay, so what exactly is happening in this impact testing? Essentially, we'll have a sample which is being placed on some anvil. Okay, so let's say this is my anvil. So I've placed a sample here and I put a pendulum. So I use a pendulum to hit this sample at some height. Okay, from some height, let's say h1, I'm hitting the sample, the notch sample. So this is the notch sample. Okay, so this is my pendulum. And this is the hammer, this part. So we're raising the pendulum up with the hammer and we are dropping it. So it comes down, it hits the north sample, and once it hits, it goes up to some height. Okay. So let me just redraw this. So the north sample has broken. Now the north sample has broken. Okay, let me just actually. Yeah, let's keep it like this. And the pendulum swings to some new height, which is given here. Okay, so this is some H2. Okay. So this difference in height, right, from earlier height till the final height, mg times the difference in this height will give us the impact toughness, okay, or the energy that is stored within this impact. Okay. So energy absorbed by the material in order for the impact test to happen gives us the impact toughness. Okay. So impact toughness. So essentially what we are doing, we are converting the potential energy of the pendulum into the impact energy. Some amount of the potential energy gets converted into the impact energy, and the remaining again it reaches to the new height h2. Okay. So this is mg times h1 minus h2, right? So this was the basic principle of impact testing. Okay. So there are two different ways people have done impact testing. One is CHARPY, another one is ISOL. But depending on how we are placing the material, we can say whether the material is under CHARPY testing or ISOL testing. Okay. Just a second. Okay. So the two types of testing are CHARPY and ISOL. So CHARPY works something like this. We have the anvil. So let me just place the sample first. So this is the sample. We have notch. Okay. And the anvil will be placed here. Like this will be the anvil. Here and here. And the hammer will be hitting from backside. Okay. This is the hammer. Okay. So in CHARPY, basically the hammer hits the sample from behind the notch, not on the side of the notch, but behind the notch. Okay. So this is Charpy's test. Okay. While in ISOT test, we will, and also the sample will be laid flat, okay, on the ground. So it's like on the sample is laid like this. It's not vertical. Okay. So if this is my notch here, the notch is here like this. Sample is placed like this, and the hammer comes and hits like this. Okay. While in ISOT, the sample will be turned around like this, and the notch will be towards the sample, and it will hit like this. Okay. So this is ISOT. Let me just draw ISOT. Okay. So my anvil will be holding a sample like this. So the hammer would come. Hammer would come and hit on the side of the impact test. Okay, like on the side of the notch. Okay, so essentially you have kept it vertically like this. The notch is here, and the hammer comes and hits like this for ISOT. While for Charpy it is kept down horizontally. You have the notch on the opposite side of the hammer, and the hammer comes and hits from back. Okay. So these are two ways impact testing is measured. Okay, and so yeah. Now coming back to the different things that can affect your impact strength. So there is a very important curve that we have to look at. Okay, so this is known as, just a second. Yeah, 1 second. I think this notes is, yeah. So if you draw impact energy versus temperature, okay. So if you draw impact energy versus temperature, we will get some curve like this. Okay. So what this suggests is that decreasing the temperature, with decrease in the temperature, would imply a decrease in the impact energy. Also, below a particular temperature, the mode of fracture is brittle. Okay, so here it becomes brittle. So here you will see brittle fracture only brittle fracture. Below a particular temperature, the mode of fracture will only be brittle. Okay, so if we change temperature, there is a temperature transition criteria. So whether the impact energy is affecting, like, is getting affected by temperature, and the fracture appearance also getting affected by temperature. If we draw them together, we get a curve something like this. So let me just redraw this. 1 second. So something like this. Again, let me draw the impact energy versus temperature. Okay, and then we can have percentage cleavage factor. So a cleavage factor has a percentage. Okay, so let me just use the right side of y-axis. This is percentage cleavage fracture. Okay, so this is my impact energy versus temperature curve. My percentage cleavage fracture curve would be the exact opposite. So let me just use a different ink. So this will look something like this. Okay. So there are different points on this temperature curve. There is a point T1 which corresponds to FTP or fracture transition plastic. Okay, this is the probability of brittle fracture being negligible. Okay, here you will only see ductile fracture. So beyond T1, only ductile fracture is what we will see. Okay, T1 and beyond T1. Now let's say another temperature T2. We will take at 50% of cleavage and 50% shear. Okay. So let's say somewhere here where it is 50%. Okay. So this is, let's say T2. This is known as fracture appearance transition temperature. Okay. So this is where cleavage and shear failure, both the types of failure, okay, will be equal. You will have 50% of cleavage and 50% of shear. So fracture appearance transition temperature. Okay, FAT. So here we have 50% cleavage and 50% shear. Okay, half and half. Then another important temperature is where it is average on of upper and lower shell. Okay, so here we have two shells, right? One shell here and one shell here. So upper and lower shell that we are having on top and bottom of this impact energy versus temperature curve. So average of that will give us some T3 value, okay, somewhere here. So some T3. So this T3 is known as ST3 is known as temperature average of upper and lower half shells. Okay. So these are three important temperature points. Now there are two more temperature points which are very, very important. T4, which is taken at CV value of 20 joules. Okay. So impact energy value of 20 joules if you are taking. We get some temperature T4 at 20 joules, which is known as ductile transition temperature or DTT. So this is the most widely accepted temperature that where ductile and to brittle transition happens. Okay, so this T4 is a very important parameter. So this is something that we can take a note of. DTT at 20 joules. Okay. Finally, T5 is the opposite of T1. Basically, here we have nil ductility temperature. Okay, so this happens somewhere here. Let me say, yeah, this shell, the lower shell, right, where it is hitting. This was T4, and this is T5. Okay. So at the lower shell, at the beginning of lower shell, we have nil ductility temperature or NDT. Okay. Here, there is fracture with almost no plastic deformation, and probability of ductile fracture is very, very negligible. Okay. So below T5, you will almost have no ductile fracture, and there will be no plastic deformation. So let me just write it down. Fracture with no plastic deformation and probability of ductile fracture is negligible. So this is T5. Okay. So these are the 5 temperature values which are very, very important to in temperature versus impact energy curves. Okay. So these 5 temperatures is something that people usually look for. Okay. So one last concept that we will see in impact energy is does crystal structure, the structure of the particular crystal system affect the impact energy versus temperature curve. Okay, so if you see some particular type of crystal structure in some particular way. So influence of crystal structure is what you are looking at. Okay, so if we draw impact energies, So we'll have one type of curve like this. Okay, then we'll have some curve which will be coming like this here, and then another curve will be coming like this here. Okay, or actually it will be higher than that, so it will be somewhere here. Okay, so which crystal structure will show which kind of uh, behavior? So essentially, low strength steels, okay, which are BCC, are usually the ones which have this impact energy versus temperature, that regular curve that we are seeing. Okay, while if you see FCC, low strength FCC and HCP metals, they will have none of this transition temperature phase. Okay, they'll not have this transition, no ductile to brittle transition. They won't have that. Okay. And high strength materials also don't experience transition. These green ones. So this is the way crystal structure will also influence this transition from ductile to brittle. Okay. Generally, BCC is the one where we see the most common transition happening. FCC, HCP, and high strength materials usually do not show that. Okay. So let's move on to the last part of today's discussion, which is composites, mechanical behavior of composites actually. So okay, just a second. Okay. Yeah. So coming back to mechanical behavior of composites. So what exactly is a composite? Is something that is very important to understand, because you should not you should be able to distinguish between what is composite and what is not a composite. Okay. Some material which is does not behave as a composite should not come into the purview of composite. So in composites, we'll have two or more distinct phases, okay, and they will combine in one way or the other, so that some mechanical property is changing as a consequence of that. Okay. So here, since we are looking at mechanical behavior, most of the places we want to ensure that the elastic modulus should change significantly. Okay. So therefore, if you see things like adding of one metal into another metal, you will form an alloy or you will form precipitates, etc. They do not come under the purview of composites, because essentially the elastic modulus does not change significantly. Okay. So that is one important criteria that you have to keep in mind. So this consists of distinct phases, two or more distinct phases. Okay. So the phases are matrix and the reinforcement. Matrix plus reinforcement. So we'll understand what these matrix and what reinforcement does for a particular composite. But yeah, before you go on, another important point. So elastic modulus should change significantly upon addition of reinforcement. Okay. Upon addition of reinforcement. Okay. So the behavior of, or characteristics of a composite will depend on what kind of matrix and what kind of reinforcements we are adding. Okay. So let me just talk about the characteristics now itself. Depends on E, the matrix, right? So what does the matrix do? What does the matrix do? It provides the bulk form. Just like an alloy or like metal precipitate systems, the bulk form is always provided by the matrix. It also protects the reinforcement. Okay. And matrix is the one that transfers the load from the reinforcement, transfers the load to the reinforcement. Okay. So it should have the capability to transfer the load to the reinforcement. Transfers the load to reinforce. And finally, it should be able to take some sort of partial deformation. Okay. some sort of partial deformation, this composite should be able to take. Okay. The second part of this composite, which is the reinforcement, also has a few roles to play. So it carries a major portion of the load. Okay, so reinforcement is the load carrying member. Okay. And it bonds with the matrix. So bonding with the matrix is controlled by this reinforcement. Bonds well with the matrix. Okay. Now why this bonding is important? For strain continuity, right? Because the strain should not, because of the strain, you should not see that the bonds break or something like that, and then the entire system splits into two halves or something like that, right? So you should not see some breaking happening. So for strain continuity, the bonding should be well done, and that is being ensured by the reinforcement. Okay. So how do we classify composites? So what are the types of composites, or how do we classify composites? So we can classify them based on matrix. Okay. So first classification is based on matrix. What kind of matrix it has? So if it has a metal matrix, so depending on that, it will have some certain behaviors. For instance, a metal matrix, what is the major property of metal? They have good strength, right? A metal has good strength and also very high in density. So why would we add a reinforcement in this scenario? If you already have good strength and high density, what do we need to improve here in metal systems? Just a second. Okay. Okay. Yeah. So in metal matrix, what is the, if you are using a metal as a matrix, what would be the advantage that we already have? So advantage we already have is it has good strength. It also has high density value. But the disadvantage is metals by itself is very, very heavy, right? Metals are usually not lightweight. So essentially you want to improve the specific strength. So you would want to improve E value or E by rho value. So that is why you will use metal matrix and something else within the metal. Okay. Another thing that we can have, okay, so just write it here, to improve specific strength. Keep in mind, I'm not talking about strength because metal by itself has a lot of strength. I'm talking about specific strength, which means that the metal strength to weight ratio is what we are looking at. Okay, we are looking at metal strength to weight ratio. Okay, so the secondary phase is added to improve strength. Okay. Second matrix could be ceramic. Now, what does ceramic possess and what does it lack? Ceramics tend to be brittle, right? Ceramics will tend to be brittle. So, but they are good in insulating, they're chemically inert and all that, right? So, why would you add something? You would add to improve toughness, right? Improve toughness. So, secondary phase improves the toughness of the ceramic matrix. And finally, you can also have polymer as a matrix. Now, what does a polymer have? It has good ductility, it is also insulating, but it has low strength and creep resistance, right? So, what would you essentially try to improve here? You would want to improve the strength. So, based on the matrix, we can see these different types of composites. We can also divide the composite, the type of composites, based on the distribution of reinforcement. Okay. So, based on this distribution of reinforcement, we can see either we have a continuous kind of distribution, where the reinforcement is continuously present within the structure, or it could be discontinuous. You will have reinforcement present discontinuously within the structure. So, if you have one structure, you can have reinforcement at some points, or you can have continuous layers of reinforcements. Okay, so it could be continuous or be discontinuous. Okay. We can also have different types of composites. We can classify them based on type of reinforcement. Okay. Okay, so it could be particle reinforced. We'll not go in detail about each of this, but you can just keep in mind. It could be continuous fiber reinforced. Okay, so it could be particles that are used as reinforcement. So you'll have small particles, or it could be continuous fiber. Or we can have short fibers. Okay, you will have short fibers. Instead of particles, now you have short fibers or whiskers. And finally, you can also have laminate. So you can have a layer, a laminate layer kind of composite. Okay. So these are the various types of composites. Okay. Also, one important composite that usually we see in day-to-day experiences, like you would have heard of it a lot in like many engineering applications. It is being used nowadays. Is carbon-carbon composite, right? So you will put carbon fibers in graphite matrix, and they give very high strength resistance and also wear resistance, right? High temperature resistance, high wear resistance, and low impact toughness. They are being used in many applications such as nose of wings, brake plates in airplane, etc. So all these airplane applications, you will see a lot of these carbon composites being produced. So therefore, these composites have like different applications, and depending on where you need particular type of composite, you will be producing them. Okay, so you will have like composites being formed for like in radial tires. You will see them, the steel belts which are being formed. Those will be composites. You will also see fiberglass, Kevlar, and all that. All of these are composites. Okay. Now they are being produced because just single material will not have these properties that can take like all the good things together and you can make one single material. You cannot have that. So you have to mix materials from different places so that all the good properties come together and you have a material with all those good properties. So this is the basic idea behind composite. Okay. Uh, okay. So now any composite can be strengthened in two different ways. Okay. So either we can directly strengthen by transfer of load, or we can indirectly strengthen due to change in microstructural properties. Okay. Now we'll not go very detailed into it, but just understand that when you're adding material into it, right? Either the reinforcement directly takes in the load and strengthens the composite, or the reinforcement causes a change in the microstructure and properties. Okay, so these two ways the composite is essentially strengthened. Okay, so with that, let's come to the final topic of discussion, which is elastic properties of composite. After which we'll move on to the problems. Okay, so let's say we have taken a composite, we are adding the matrix and reinforcement together. Okay, now what is happening here? The mass of the composite MC is equal to the mass of the matrix plus the mass of the reinforcement, right? Now volume of the composite VC would be equal to volume of the matrix plus volume of the reinforcement plus. Now due to mixing of this matrix and reinforcements, you will see formation of voids, right? So this voids also is something that we have to take into account. Why? Because you will not see a perfect one-to-one matching between matrix and reinforcement. Some places you will see voids being formed. Okay. So density of the composite will be equal to mass of the composite divided by volume of the composite, or you can write it as Fm rho m plus Fr rho r, right? Where actually let's use small f rather than capital F. Yeah, small f. Where Fm is the ratio of Vm by Vc and Fr is, let's use small r actually. Okay. So this is the density by rule of mixture. Density of a composite. So depending on how the composite and reinforcements are arranged and how we are applying the load, we can either find the two extreme conditions for the elastic modulus for a particular composite. Okay. So one condition could be where you have isostream. Okay. So what happens here is you have okay, just try it. What we can have is let's say this layer is matrix. Again, every alternate layer is matrix and composite. Okay. So if you're applying the load like this, what is happening is both matrix and composite is getting pulled together. So you have condition something like this. Right? So this is my isostrain model. Okay. So this gives me the upper bound for elastic modulus. Okay. So this is known as void model, also known as void model. So this gives me the upper bound. And known as void model. So here the upper bound, the EC, would be equal to FMEM plus FREM. You can see from the figure itself and you can figure out how this is because they are both being pulled together, right? So the sum, the elastic modulus for the composite will be sum of the individual effect of individual matrix and reinforcements elastic modulus, right? Now another way in which the composite could be arranged, which is the isostress model. Okay. So here, essentially, we have the composites. Just draw it. And matrix being arranged something like this. So every alternate layer is composite and matrix. So you're applying the stress again like this, or load like this. Okay. So this is isostress model. Now here, how we are having the arrangement, we are seeing something like this. Right? So this is my EM, this is my ER. Right? And the stress is being applied in both the directions. So this is known as the lower bound of the modulus. This gives us the lower bound of the modulus and commonly referred to as Ruiz model. Okay. So Voigt and Ruiz have given these two models, which gives us the upper and lower bound of elastic modulus for a composite mixed with the matrix and reinforcement. Okay, so using the elastic modulus of matrix and reinforcement, we can find the bound of the two cases. So now my new elastic modulus would be something like this: EM times ER divided by FMER plus FREM. Okay. Basically, what is happening here is 1 by EC will become equal to 1 by FMEM plus 1 by FRER. Sorry. So essentially, this combination will give us the lower bound for the elastic modulus. Okay. So with that, we'll come to the end of the discussion part. Now let's move on to the problems for today. Just give me a second. Let me check if everything is correct. Okay. So coming back to the problems. So first few problems are just theoretical. So Brinell hardness uses, we all know Brinell hardness is the one which uses steel spheres. Okay, so second option is the correct one. Now they have told in a hypothetical curve given below for impact testing, the correct combination for A and B is, what is A and what is B? So A could be any HCP or FCC material. B is a BCC material, right? So we'll see the combination where B is BCC and A is FCC. So if we see the first option, B, A is mild steel. So A, that is wrong because mild steel is BCC, so that could not be correct. A is nickel. Nickel is correct because nickel is FCC. B is low carbon steel, could be possible. So second option could be possible. A is chromium. Now chromium is BCC, so it could not be A. So fourth option, A is aluminium. Aluminium is correct. Aluminium is FCC. And B is chromium. That is correct. This also could be an option. Fracture surfaces of the same alloy are shown below from impact tests conducted at 3 different temperatures. Which one is true? So based on shininess of the surface, we can say that T1 is lesser than T2, which is lesser than T3, right? So we know that granular shiny texture would happen at brittle or low temperature, right? So T1 would be lower, while you will see a shear character or fibrous character or dull character for ductile cases, which will be at higher temperature. So T3 would be highest. Okay. Fourth question. NDT is defined at temperature below which fracture is 100% brittle. That is correct. NDT is nil ductile temperature, right? Next is fat is a temperature where fracture is 50% ductile and 50% brittle. That is also correct, right? FTP is a temperature at which 100% ductile failure is observed. That also is correct, right? So FTP is what? Fracture transition temperature, fracture transition plastic. So that is where 100% ductile is observed. So before that, fat was fracture appearance transition temperature. And finally, ductile transition temperature is a point where impact energy is 20 joules. That also is correct. DTT is where 20 joules happens, right? Okay, so the next question is a problem. Find the Brinell hardness number if the load is 2000 kgf, indented diameter is 1 centimeter, and diameter of indent impression is 0.2 centimeter. So they have asked us to find the Brinell hardness number for this particular case. Let's see. So the formula is two P divided by pi D times D minus root of D squared minus D squared. Right? This is the formula. Now D, capital D and small d are in mm, P should be in kgf. So it will be, next slide, 2 into 2000 divided by pi into what is D? 1 centimeter. So 10 to 10 minus root of 10 square minus 2 square. Right? This is what you have to calculate. Let me just calculate. My screen not changing. Let me just check. I think there's something wrong with my screen. Just reshare it. Yeah. Something is, why it is stuck? Just a second. Okay, I think now my screen is okay. Now it's working. I think there was some error. Screen was not moving. Okay, so yeah, I hope you were able to see the third and fourth problem. But anyway, I'll just show it again. So third problem, they asked what is the temperature, like which temperature, like what is the arrangement of temperature. So we know that T1 would be lesser than T2, which will be lesser than T3, because if we are having a more granular structure, then it will be brittle at lower temperature. While if you are having a more shear, fibrous or dull character, it will be more ductile at higher temperature. The fourth option, as you can see, all of them are correct. I'll not go through it again. You can just check the notes again. So all the options are correct. So the fifth question, they asked us to find the Brenner hardness number for the particular case. So we know the formula, the values are given to us. So after substituting, I'm just calculating it. Just a second. So I'm getting the final answer to be 630.2. So this is second option. This is correct. Next question. Apart from impact and hardness test, there are also something known as compression test, okay? And they are carried out to measure the compressive properties of metals and alloys. They have given us the formula for finding true strain and engineering strain, okay, using different cases. Now, they have asked us, a cylinder is compressed from 30 mm to 10 mm, okay? Find the magnitude of true strain. So here 30 mm would refer to H0, 10 mm would refer to H1, okay? So if we substitute, epsilon will be equal to minus ln of H0 divided by H1, right? Or if we want to forget about the negative sign, because they have told us to reverse it, so we can just write, okay, let's just take the negative sign for now and we'll take care of it in the end. Negative ln of 30 divided by 10, right? That will be equal to, let's just calculate.
So 1.09 is what I'm getting, negative 1.09. But we can ignore the negative sign as the question states. Right. So this is the correct option. Okay. 7th question, purpose of the matrix phase they have asked. So what is the role of matrix? We have already discussed. It shares the load with the reinforced material, that is correct. It binds the reinforced material, again correct. Deform partly, that is also correct, for effective load transfer. And it improves the Young's modulus of the composite, that is wrong. In a situation where we want good insulation on the material and surrounding is chemically active, which type of composite is the most suitable to use? So we know that good insulation chemically, like if the surrounding is chemically active, we want something that is not chemically active. So ceramic would be the best one in that case. Right? Okay. Next question. If it is given that that in a composite volume fraction is of matrix is 0.79, okay, so FM is 0.79, and reinforcing phase is 0.19, so FR. So we have something like 0.02 which is left, then which is true? What is that 0.02? We know that 0.02 could only be the void, right? So the only option that talks about void is the first one. So that is the correct one. All other options talk about it is not being possible or something else for that 0.02, which is not correct. So let's move on to the final question of the day. So they have given us a composite made using fiber reinforcement as shown in the figure. Okay, and load is applied in this particular way. So load applied along the axis of the cylinder. So their load is being applied like this. So this is what kind of condition? This is isostrain condition. Right? So we can write EC. So they have asked us to find the EC, right? Yeah. So EC will be equal to FM EM plus FRER, right? So have they given us a value? FM is, so FR is 0.25, so FM has to be 0.75. We are assuming there is no void. Okay. Into 100 plus FR is 0.25 into 200. So 0.75 into 100 will give us 75. 0.25 into 200 will give us 50. Right? So 70 plus 50 will give us 125 GP. So this is the answer. Okay. So I hope everyone is clear on whatever we have discussed today. What are the various things that we have covered. So with this, we will come to the end of the discussion session for today and the discussion session for this course. I hope all of you were able to follow through whatever we have discussed from the first class till this class. In any case, if there are any doubts, you can write to me, or you can also put it up on the portal, the NPTEL portal, where we'll be clearing your doubts anyways there. So you can put that up there also. And with that, we'll come to the end of the course Mechanical Behavior of Materials Part 1. I hope you all had a good time, and we will hopefully meet again in some different course. Okay. With that, we'll come to an end. Thank you.